All right, guys. We're gonna jump ahead. We just said that this was chapter 3, but we're gonna jump ahead to a section in chapter 6, and that's gonna be like the next. There's a lot of stuff to do with projectiles. It's kind of important topic, but we're jumping there because it's so closely related to what we've been doing. We just got to make some slight adjustments to some of the formulas we're doing, and it's a topic that's part of a chapter called Motion in Two Dimensions. Okay, other parts of this chapter we'll get to at a later time. But pretty much everything we've been doing so far has been either just on this axis or just on this axis, right? Free fall, dropping, throwing stuff just straight up and down, right? Or something moving like this. Yeah, we had some things like this, but that's still really one just slanted axis, right? So we're going to hit some motion in 2 dimensions, and one of the most important times that happens often is projectile motion. Projectiles are just anything that's like shot, fired, or thrown through the air, anything like that. It could be something that rolls off the table, like that. Later next week, once you learn how to use the formulas within this topic, you'll be able to predict exactly where something's going to land that rolls off the table. That's part of the lab, part of the target lab. But there's some background stuff we got to prove before we jump into the math and the idea behind it. And we're going to start with a question. We'll use my dark gun. Alright, so we're going to, in a moment, I'm going to take 2 people. Do I have anybody want to volunteer? Noel, okay. Let's see. Somebody gets the gun, somebody doesn't. You're going to not get the gun, okay? So, I need another volunteer. Alright, you'll get the gun. Alright. It's not that I don't trust you. I don't trust her. Okay. Anyways, Mike. Right away with her. Anyways, okay. So we're going to ask a question. Just think of the answer to yourselves. Don't answer it out loud, okay? So we're going to give Ashton this gun in a minute. And I'm going to ask her to point it horizontally and fire. Okay? Just down the aisle. Okay? And at the same moment, listen, at the same moment, I'm going to ask Noelle to hold this dart, the same exact kind of dart that's in the barrel that'll shoot out of it. She's going to hold it at the same level of the barrel. I will count to 3. And on 3, you shoot and you drop. The question is, which one hits the ground first? All right? Don't answer this out loud. Just come up with an answer yourself in your head, what you think's going to happen. All right? We'll do it and see what the result is. Now, when you shoot it, make sure you pull the trigger in to a little bit, so when I say 3, it immediately shoot, so there's no like time of pulling it back. Okay? You'll feel it. There it gets to the point where it's so tight. All right, so come on, you get down the gun. Nerf gun. Yeah. You want to round me into Nerf gun? Okay, you like that. Now you're going to stand beside her. You point it out completely horizontal. All right. Don't go yet. I want you to hold that one. Listen. So everybody can see you're holding it right where the barrel is. All right. I'll go this way. All right. So that's pretty much the same level, right? Yeah. So we're going to count to 3. On 3, you let go, you shoot. 1, 2, 3. Now, Carson's book bag got in the way, so we got to do that all over again. Right. Do you want to do the gun this time?
He was hit for 3.
2. I didn't think that test. I didn't test anything. All right, let's try it again. Right down the middle of that, okay? You gotta hold it up to the exact level of the barrel, okay? Ready? 1, 2, 3. Whoever takes this one to do. It must be the volunteer.
See, I would do it.
Hold on. Try this again. Ready? 1, 2, 3. What happened? Looks like it was pretty close at the same time, right? All right, you guys sit down. All right? Now I got something that the timing will be a little bit better. Similar idea, smaller scale. And you'll be able to see both right here right away. I got just a little spring-loaded thing here and 2 ball bearings. One of the ball bearings is going to hang off this end. And if this has a hole in it, it'll slide out and be able to drop at the 100% exact moment. That was pretty good what you got to do. It was pretty close to the right time. But this should time it perfect. This spring-loaded apparatus is going to kick this one to the right and drop this one at the same time. So this should work out 100% perfectly the time. Exactly the same time, right? So how do we explain that? Exactly. Because a lot of times we might think, well, the one that's fired, that's going to hit the ground first. But we already know stuff about free fall. That's why we're jumping into this stuff right now, because it just makes sense to do it now. When something's in free fall, gravity only acts on what axis? Yeah. Vertical, or the y-axis, right? So basically what this little thing just proves, this demonstration proves, is that does gravity really care what's going on this axis? No, because whether something was shot horizontally or just fluff drop, didn't gravity pull both of these to the ground at the same time? Now what if we had a really big open area that was completely flat? And what if we did this with a real gun and a real bullet? Would we have the same result? Some people are shaking their heads yes, some people are shaking their heads no. Well, if you think no, what would be the difference? Well, the bullet definitely goes faster if it gets shot horizontally, right? Does that really matter? Think about it. This one went a lot slower than that one, right? Because this one only shot from here. So we had the same result with both this one and this one, right? If, I don't care how fast that bullet's going, if we give it its initial speed completely horizontally, does gravity care? No, gravity's just pulling it downward. As long as air resistance is negligible, just like when we talk about with free fall. And for these kind of objects, they pretty much are from a small drop like this. Even these darts, that actually could be pretty greatly affected by air resistance. For a small fall, like in this classroom, basically not a big deal at all. All right, we could say it's negligible for them. So, although we can't use a real gun and a real bullet, we might get in trouble for that. At some point, when we have a little extra time, maybe later this week, I won't watch the whole episode, but if I could find like the result on YouTube, there was a Mythbusters a few years ago that were the first to actually do that like full scale with a real gun and a real bullet. And it was much trickier because it's not like you could see a real bullet. The one that's fired especially, right? The one that dropped, no problem. It's going so fast, you can't see it. So they had to use like high-speed video, and there was a lot of issues along the way, but in the end, they proved what we just proved right here. And what this then proves, like, even mathematically, once we move into the problems here soon, is that we say that a horizontal motion and vertical motion are independent of one another. Because it didn't matter if one was fired this way and one was dropped, right? So that means for something that's considered a projectile, that's moving in 2 dimensions at once, basically we're allowed to treat it on paper, mathematically, as if it's going this and this, like separately, but it's really going on at the same time. So anything in 2D motion are moving both horizontally and vertically at the same time. But because of the nature of what this experiment isolates and allows us to see, we could just look at, okay, let's just find the horizontal stuff. What's going on with that? Let's just find the vertical stuff. We could bring it all together, though, because it's all happening at the same one. At the same time. Everything's moving in 2D, but we could treat it as, okay, what is it just going this way, or what is it just doing this way? Did it all come together at the same time on paper when we're doing the problems and breaking it apart? Also, for the horizontal motion, we'll put a lot of this support stuff in our head. So, this way for the one that is shot, whether it was on this, whether it was the one that was shot to the your left, my right up here, or if we're doing this with a real gun and a real bullet. Once I pull the trigger, or once this thing shot the one ball to the right, how do you think it's moving horizontally until it hits the ground? Well, it makes sense. So when I shoot horizontally, not vertically, just focus on the horizontal motion. When the dart comes out of this gun and shoots out, as long as we can neglect air resistance, how would it move? That's stuff we learn. Well, I don't want to move. I don't care about down right now. I care about across, horizontal. How would it move? On the y-axis, if you just said constant. Put it this way: where does the acceleration come from? In a gun like this, it's like a burst of air, right? It shoots it out. Once it leaves the barrel, is that burst of air affected anymore? That's what got it into motion. And if air resistance is negligible, we'll go on with that. We're only going to work on situations where that's negligible. Once this thing's fired, if it was fired, I'll make up a number. If it came out of this barrel at 3 meters per second, how fast will it continue to go on this axis? 3 meters per second. Because gravity only acts on what axis? This axis, right? But horizontally speaking, this thing will keep traveling at 3 meters per second or whatever it is, constant until it strikes the ground. Does that make sense to everybody? That's like if I just throw a ball. Once I let it go, if I throw it completely horizontal, once I let it go, there's nothing else accelerating it on this axis, is there? So therefore, once I've released the force accelerating it, as long as air resistance is a non-factor, it will continue. If I throw this, let it go at 5 meters per second, it'll continue going 5 meters per second, not faster, faster, not slower, slower. On this axis. So what does it do on this axis? Yes. It will not decrease. If I shoot it horizontal, or throw it horizontal, it only has one way to go, and you'll get faster on the way down. By what number, though? 9.8, right? It's little g. It's in free fall on this axis. So it's constant on this axis, free fall on this axis, and that'll guide us into what equations we're allowed to use. We already know them. We just got to make them a little more, what we'll say, axis specific. That just means we'll take a lot of the variables we knew and make them x's and y's instead of just plain old d's. Because there'll be a d on this axis and a d on this axis. We don't want to get them confused. So we can handle all the math behind all this stuff, predict where things and projectiles are going to hit based on really the stuff we've been using. Now there are two general types of projectile problems. This example had to do with horizontal fire projectiles. They're typically the easier of the two to take care of because there's less going on. So today and most likely into tomorrow, we're only going to care about horizontally fired. That's why in that example, I told Ashton to hold the gun completely horizontal, right? If she would have held the gun like this and Noelle still did what she did, would we have the same result? No. This now becomes projectile fired at an angle. We need a little bit more math to handle that. We need some very basic trig, which probably like later tomorrow or Wednesday at the latest. We'll do a little quick basic trig review. You should all be good with it. Even if you just have trig this year for the first time, let's just soak in some of the stuff that you probably didn't tell you to do. All right. But anyways, still most things are the same, especially in mathematically. When we do projectiles at angles, we just got to add in a little bit more math because of the angles involved. But as far as today goes and into tomorrow, we're only going to worry about things fired horizontally. Things rolling off a table horizontally. All right, so we'll just refer to those as horizontally fired projectiles. So I'm going to go to switch over to the notes. Okay, so I will post these same ones, so it doesn't matter. Actually, these are in a printed form for this topic. But some of the most important stuff we just discussed right there is number one, what a projectile is. An object's fired or shot or however it's put in motion through the air where it's going in 2 dimensions, not just on one axis. Okay, so like yeah, we could fire something straight up, and we've already done that, right? That's just regular old freefall, right? It's technically, usually we don't use the term projectile until we're moving in 2 dimensions. This way and this way at the same time, okay? What we just proved with some of those demonstrations is that the horizontal motion is completely independent of the vertical motion. So gravity doesn't care if it's moving on this axis or if it was dropped from that axis. We still have the same result. They hit at the same time, right? And that means we could use some old equations, but look a little different. So this is what I was saying. So x-axis, you said it moves constant, right? What's the only equation we have that matters when something's going constant, or otherwise when it's not accelerating? V equals whatever what? D over T. Well, I say that doesn't look like it, but it really is. Instead of saying D, since we have 2 axes now, we gotta be a little more specific, and this is a common way to do it. Instead of D, we're gonna say delta X. Delta means change in. Remember going over that earlier in the year? All right. Change in X position, is that what that means? And a change in position, we learned a long time ago, is called displacement, right? So that symbol altogether right there basically just means horizontal displacement, delta X, which we used to just call D. We just got to get you a little more specific in this topic with it, okay? And instead of just a regular old V, we'll subscript with the X. That means horizontal velocity. But just like any time we use the constant velocity formula, there's not an initial or a final subscript, is there? Because that would not needed. If you're going constant, your initial and final stay the same, so we don't have to distinguish between them, okay? At any time t, you would be going on this axis for a projectile. Right? Like we said, the reason why is once you throw and let it go, there's nothing on this axis to speed it up or slow it down until it actually hits the ground, right? So that's our one equation we have on the horizontal axis. But we come over to the y-axis. While these projectiles are flying through the air, they're affected by what on this axis? Gravity. So guess what we have? Our uniform acceleration or kinematic equation. But everywhere we would have A, we have what there? No. G, because this is free fall, right? Free fall on that axis. It's the same as when we did regular 1D free fall on that axis alone. It just happens to be moving this way as well at the same time. It's simply free fall. Now, same idea over here. Everywhere we used to see a D, we now see what symbol? Yeah. Delta Y. That just means change in Y position on this axis, or in other words, the Y displacement. All right? And on all our V's, we just got an extra subscript there. There's still our V finals over the initials. There's just a Y there with it, right? Just to make us realize this is just on the Y axis. All right, yeah. Oh, that's the typo. I'll just draw over that. That should be a plus. That second equals. I never thought that. Here, I'll just write right over top of that. That's just a plus, yes. I can't get rid of it equals without redoing the. That should be a plus right there. Then. Those are all the same 4 equations. They're just a little bit more specific. Okay. Just a diagram to give a visual on this. I'm going to draw some vector arrows in the diagram. So to represent this as an idea, rather than in words, we often use diagrams, right? So if I were to draw velocity vectors on this diagram at these 5 positions, right? So this you can imagine this being like a ball rolling on a tabletop and then rolling off, okay? So however it got rolling gave it some velocity, right? Maybe it was rolled down a ramp and then it came to the bottom of the ramp and now it's on the tabletop and now it's going to roll off. So if what we said is true, and it is about going constant horizontally, if I drew in horizontal velocity vectors at any moment, they should all be about the same length. Because remember when about drawing vector arrows, we said in the past that there's length should be relative to their magnitude, right? Or how fast it's going. So to keep this diagram general, like each one of those represents Vx. And even throughout rolling off the table, or being fired, however this thing got in motion, until it strikes the ground, it's going the same on this axis, right? So we could plug in any number there. If it was going 10 meters per second as it rolled off the table, right here, 10, 10, 10, all those vector arrows to have a complete vector diagram should look the same, right? On that axis. But on the y-axis, well, in this frame and this frame, this ball has not left the table yet, has it? All right? But here, here, and here, it's off the table, right? So what happens to things as they fall? They get what? Faster. So the Vy vector arrow, if we were asked to draw that in, should get longer and longer, right? Because at any given moment, the Vy at that moment, the vertical velocity, it's in free fall and it gets faster and faster and faster, right? And of course, notice at the moment it left, it's still on that table right there. This isn't really the moment. This is like the moment right before, right? But the moment it leaves, like we would say Vy initial, and this is going to be important. I'll put a star over here and write in. Vy initial, it's like it was dropped, so it's equal to what? 0. And again, isn't that kind of what our demonstration just proved? Is it, at least vertically speaking, something that gets fired horizontally like out of that Nerf gun compared to the thing that dropped? We always said in the past when we dropped something, V initial was what? 0. So this did the same exact thing on that axis, right, as the one that dropped. It fell and hit the ground. Yeah, it hit over there, but it still hit the ground. Vertically, they all got there at the same time, right? So therefore, every time we have a horizontally fired projectile, this is something they're not going to tell you. Just the fact that you identify the problem as a horizontally fired projectile, we say Vy initial equals 0. You got to remember to put that. All right? We do eventually have to be careful. This will be something that's not true when we fire it at an angle. But if it's horizontally fired, rolls off a tabletop, something like that, that's always 0. That's one of our givens. And just putting some of these other symbols from the equations on this diagram, this would be our delta y. That's how far it's going to fall, right? That's going to be its vertical displacement. Just like with free fall problems. If, obviously, for something fired horizontally, it only has one way to go vertically, and that's where? Down. So, if I tell you that this tabletop was 3 meters high, that would be a high table. Let's say this tabletop is like 1.2 meters high, all right? In the equation, since I'm going to fall down that far, what do you got to do to that number? Make it what? Negative, right? Because in that equation, in those equations, if you put delta y as like 1.2, you're trying to tell the formula that it rolled off the table and went up, and that's not going to happen. You'll have a mathematical breakdown. So we still got to worry about things like that. Since we are in free fall, we could still always say G's negative 9.8, right? Meters per second squared. That's always going to be true still for all these problems, whether we're horizontal or not. And the delta x is just going to be the horizontal displacement, in this case from the base of the table to wherever it lands over here, right? That's what delta x is going to represent. Make sense? As long as we understand what those pieces are. What time's the star ring? 36. So that's pretty much all the background stuff for this. We're going to try to get through a problem. If we get through the whole thing, you'll have a homework problem or two. If not, we'll have to do more. I'll see. Might as well jump right into it. Yeah. Yeah. Vx. Right. So whatever it is, if it told you something like a ball was rolling on a tabletop at 3 meters per second, and it rolled off the table, then even during the projectile motion, once it rolls off, it's still horizontally going 3 meters per second. Yes, like this way. Absolutely, you'll see that once we put some the problems to it. Absolutely. Because just common sense will tell you the slower this thing's rolling, if this rolled slower, it would end up probably somewhere like right here, right? If it rolled extra fast somewhere here, just like we did 2 scales of this demonstration, right? The dart gun shot it faster, that dart went back like Carson, right? But the one I did on the smaller scale with just the ball bearings, it was just a little flick of a spring-loaded thing, and that ball didn't go nearly as fast, so not nearly as far, right? So absolutely, that has an effect on it. If it had any VX, non-zero VX at all, it can't drop straight down. It would go at least a little bit out, okay? If it went straight, the only way to go straight down is to drop the press, okay? And then it would just be a straight up one-dimensional free fall problem, okay? All right, so anyways, what we'll, just a little look ahead to a lab we'll get to next week, most likely. By being able to measure and figure out a lot of this stuff of a real ball rolling on your tabletop, you're going to have to place a target on the floor. And your grade is solely determined by where it hits on the target. It's like set up like a bullseye. So if you hit it right in the middle, you get an A. If you don't hit it at all, you guess what you get. We'll talk about more of that later. All right, so this is enough to know to jump into a problem. We're going to go to page 150 and do number 1 as an example, okay? So open up your books to page 150. If we make it through the whole example, may not. You might get a couple problems around one. I prefer it that way. Depends how much damage it does. Okay, now since I already have a diagram, a general diagram to refer to, I'll just flip back to this generic one. I'm not going to redraw a new one, okay? Because the same diagram fits the idea of what's going on in this one. It says a stone is thrown horizontally at a speed of 5 meters per second from the top of a cliff that's 78.4 meters high. Now, since we have 2 axes, it's best to set these problems up with 2 columns of givens. It's best to do an X column and a Y column, so you don't get your numbers confused, right? Something that is X specific can't be also in the column that's Y specific, okay? There's only one piece of information that could fall into both. It comes back to something I said earlier. Everything that happens this way is independent of this way, but they all happen to be happening at the same time. Time is what brings everything together, okay? Both things could be thought of as separate, but in reality, they're both happening at the same time. So there's no such thing as like a Tx and a Ty. T is a scalar, it can't be given directions or axes or something like that. Everything occurs during this, all right? So what we know, we throw it horizontally. So as soon as you know it's horizontal, what did I say was 0? Vyi, right? That's right, just be as specific as possible. So right away I see that, I should put that down, Vy initial 0. And I should also know immediately, I could do this before I even read the problem really, on the y-axis we should know we're in free fall as long as we know it's a projectile problem, right? So I put in negative 9.8 meters per second squared. And it tells me the horizontal speed is 5 meters per second. That's pretty clear what I list that as. Right? Not x, okay. Vx, right? 5 meters per second. And one last piece of information, it is 78.4 meters high. What is that? Yes. Careful. Meters. Anybody else? 78.4 meters high. What given is that? If it's meters, it's got to be a D, but we renamed D's, right? Delta Y. And like I warned you a moment ago, you got to do what to this number? Make it negative, because it could only fall down that if it's rolled off the table, right? Or thrown, not rolled off, this one is thrown horizontally. Either way, it can only go down, so we've got to make that negative. All right, so part A of this problem. Now I am going to warn you, this is the earliest problem they give you us on this in your book. Most of the time, they will not directly ask you for T. This problem does. Part A of this problem does. This is what you usually have to do in most problems. Find T to find something else. We should always keep expecting, as you've been told this before, sometimes you got to find something they don't ask you for to find something they do, right? Beyond this problem, most of them aren't going to directly ask for T. You need to figure out how to get T. How do you do that? It depends. They'll mix it up. We're either going to have enough information in this column or this column to find T. Remember, both happen at the same time, but you're only going to have enough initial information in one column to actually order one. Question. Yeah, we're at the top of the cliff. We throw it from the top. That's how far it's going to fall down, right? Throw it off the cliff horizontally. Now, once we get into angles, there's a possibility we threw it up, and we got to worry about more stuff then, but we're not there yet. Okay, you throw this horizontal, it only has one way to go vertically, and that's down, right? Launch horizontal. Okay, so let's figure out how long it takes. Doesn't seem like we have much information in the X column, right? So it'd make the most sense to look over here, right? We got to find T, and we're looking good because we have three things over here. What equations are we allowed to use on this axis? The kinematic ones, right? We find the right kinematic equations that were just slightly adjusted for this topic. So if we go to kinematic equation 2, delta y equals dy initial t, with dy initial 0, so that's whole term's gone, right? Plus 1/2 gt squared. If we solve that for t, we multiply each side by 2 and divide by g and take the square root. Plug in our numbers. This right here is where, if we didn't make that 78.4 negative, this is where we'd be in trouble. Because then I'd be stuck, because I'd be trying to take square root of a negative, right? That negative will cancel with the negative on the 9.8. And we should get close to 4 seconds here. So really, nothing we haven't done before, right? That was just, again, I'll say this a million times. This just happens to be in free fall on this axis while it's also moving this way, right? It's the only difference. It's really not that big of a deal. Alright, if we're okay with that part, let's go on to part B. Part B says, how far from the base of the cliff does it hit? What is it asking me to find? Let's go back to my generic diagram. How far from the base of the cliff would be what variable? It's up there looking right at you. How far from the base of the cliff? Where's the base of the cliff? Here, right? How far from it? Well, there's only two distances involved, right? They already gave me delta y. This has to be what? Delta x, right? That's what they're asking me for. And we only have one equation for delta x, right? Since we're going constant on that axis, is delta x equals vx times t. And, well, I know vx, right? That was 5. That was in our givens, right? And remember, the t is allowed to cross over because this is all happening at the same time. Now, we do always say we try to solve problems using only givens if possible. The only way possible to do this problem is to find t and use it. We already did that, right? So we're going to plug in that same t we just found, and this is a really easy problem too. 5 times 4, it's going to land 20 meters from the base of the cliff, horizontally. Make sense? Now, we're going to run out of time, so I'm not going to do part C till tomorrow. But with what we've done so far, that should be enough to give you a start on a couple problems. I want you guys to try tomorrow, just numbers 2 and 3. Page 150, numbers 2 and 3. Give them a shot. Don't worry if you get stuck. All right, we'll go over them. Stuff new. Try it the best you can, okay? It wasn't thrown up, it was thrown horizontally. That's the first thing we said, okay? Once we throw it up at an angle, we got to consider more things, so that's coming later. That's just like shooting that horizontally. It's just like ball rolling off the table. Yes, because it only has one way to go down. If it's going horizontal. Delta X always will come out.
Assuming the way I threw it's the positive direction on that axis, that'll always come out positive. Okay? Because it always goes that pound weight, right? See you guys.